So today is the last lecture, and 12 hours of lecture, it's a lot of lectures. And I thought in 12 hours I'll be able to say everything I could ever think of in the subject. And at the end I realized I really couldn't say very much of anything. I've said a lot of things, but there were so many things I didn't get to talk about, which is okay, you know. And so I kind of rethought of what I would try to do today. I wouldn't try to do some kind of huge amount of different things. And I thought about everything yesterday, and I had this sort of idea about what I should do today. And now I say, I know what I should have done in this course. I should have made it more focused in a certain way. But anyway, that's like an afterthought. So what I decided to do is I decided I would, I've been trying to prepare people to understand sort of research level kinds of problems in the subject of constant mean curvature surfaces in like R3 or 3 manifolds. And so I think I've done enough that you'll understand at least part of a talk that I gave here at IMPA. I've changed it a little bit, but I gave a talk in the beginning of January about minimal and constant mean curvature surfaces. And so I'm just going to kind of go through this. It's very time-consuming to modify things. So I'll just kind of go through quickly some parts of it that we already know and explain other parts I didn't, for example, get to explain at all in my talk at the conference on hyperbolic geometry and minimal surfaces in January this month. So this is a familiar slide, so I'm going to go fairly quickly through some of these. Okay, so we have 8 surfaces. We have these classical examples. We have a definition, which we've already covered before. But it's kind of nice just to see it in perspective. So this is very introductory, right? Minimal surfaces, critical points to area under compact variations. And we have our very classical examples, which are useful. They're useful for various reasons. They're tools. You can think of these classical examples actually as tools for understanding general problems about surfaces. So one of the themes of my lecture today is somehow universality of certain things that happen. So we have somehow like local picture theorems. What do things look like on a very small scale? Complete embedded minimal surfaces in R3. And we have some understanding of that. So I'm going to try to go in this direction of there's some very general results that tell us about everything. And somehow these classical surfaces help us understand everything. So we're going to try to see that theme today. Okay, and this is again our nice slide. So here's the first thing I wanted to try to explain. How do these things we've been talking about, like local pictures and so forth, how do they help us understand just a very classical question? So it is, you look at the round sphere in R3, the round sphere is simply connected and embedded. And question is, are there any planes, any simply connected, complete, embedded, constant mean curvature surfaces in R3? Non-zero constant mean curvature. So we have like cylinders, nice, properly embedded, but they're not simply connected. And we have, it turns out, interesting, complete, properly immersed surfaces which are conformally the plane. They're conformally the complex numbers, the complex plane. So, but they're not embedded. So it's hard to embed planes in R3 with constant mean curvature. So one of the things to try to understand is why is this hard to do? In particular, it turns out you can't do a whole plane. So you can't put a plane in R3 with a complete injectively immersed plane with non-zero constant mean curvature. So we're going to see some of these ideas here. So I'll go over some of the ideas as to why that's the case. So once you prove that you can't put planes, Of course, there was some previous history on this. For example, a long time ago, motivated by something Harold asked me, I figured out how to do this if the surface was properly embedded. Okay, so we had that extra word proper versus complete. So there's a kind of a klobby-yow problem involved here. Are complete examples complete embedded? Are they always properly embedded? If they are, we know a lot more things. So at least for minimal surfaces, we did know complete embedded was properly embedded for finite topology. Okay, and then when you're properly embedded, Harold Rosenberg and I, we proved that if you're not a flat plane, then you are a helicoid. So you have the plane, you have the helicoid, and you have the round sphere if you allow yourself to be minimal. So constant mean curvature, but maybe not zero. So that's the complete classification. So what was kind of missing was the non-zero constant mean curvature case here. So so it was a complete understanding of complete embedded H surfaces. Okay, so that's where we were. Like I said, these are just from this talk I gave at IMPA. Okay, so this is just kind of a review. I've been talking about a number of different results, and this is just a summary. So I don't know how familiar you are with all those results. This is just kind of a summary. So for example, in this picture, we have the catenoid, we have a Delaunay surface, we have the helicoid. So this first result was a little more general than I stated in the previous slide. It says that there do not exist proper one-ended, that means one-end surface, constant mean curvature 1, green refers to the mean curvature, finite genus, and it should be finite genus, right, in R3. Finite genus really means finite topology here. Okay, so you can't take a plane with a handle either. Not only cannot put a plane in space, you can't put a plane with a handle if it's proper. Okay, then we have this wonderful result of Korovar, Custer, and Solomon, which used sort of a result that I had, that the annular ends are cylindrically bounded. So when you have a proper annular end, it's actually contained in a bounded distance from a proper arc, a proper line in, or it's a bounded distance from a line in R3. And then you can use some translation techniques, which I'm going to talk about today, in much more generality to prove that you're asymptotic to a surface of revolution, and then you are asymptotic to a Delaunay surface. Okay, then we have Lopez-Ross, which says finite genus, finite topology, genus 0, minimal surface of finite total curvature, or planes and catenoids. You can't take a sphere with 3 points removed, have finite total curvature. And interesting, this actually goes back, there's a Lopez-Ross result, but there's an earlier result that I did with Lucasio George in Fortaleza. Well, we proved a version of this, but only if you have 3, 4, 5, or 6 ends, I think. Or maybe 3, 4, and 5. So you take a sphere, you remove 4 points from it, it does not appear as a complete embedded minimal surface in R3 of finite total curvature. But then they have this very general proof that works for any number of ends. Our proof didn't work for 6 ends. Okay. Okay. All right. So then we have Shane's result, which says if you have finite total curvature, genus minimal surfaces, 2 ends, they're catenoids. It'd be nice if I had time to prove that, but I'm not going to have time. Then you have this nice result of Cullen, which relates finite topology to being proper. Proper and finite topology, minimal surfaces, but you have to have more than one end, then they all have finite total curvature. Very beautiful, nice result. And then you have this result I mentioned before with Harold. If you are simply connected, minimal, and you're proper, you are in fact plane or helicoid. And then you have the solution of the Calabi-Yau problem for finite topology minimal surfaces that are embedded in R3, which they prove that complete embedded minimal surfaces, finite topology, are proper. So that kind of gives you, lets you remove some of the hypotheses. They solve the Calabi-Yau problem. Okay, so we want to just focus on some of these things that continue, Calabi-Yau type problems that continue to be true for H surfaces. So complete, the first result, we mentioned this before, complete embedded H surface in R3, finite topology, always has positive injectivity radius. Okay, now if you have positive injectivity radius, it turns out you're always proper. Okay, Harold and I did this for minimal surfaces. Okay, so when it's positive, actually interesting, you actually get also a bound on the second fundamental form. So when H is positive, then positive injectivity radius is equivalent to having bounded second fundamental form. Okay. All right. And I'm going to talk a little bit about that. It's like not much. Okay. So, and like I say, these results were known previously for minimal surfaces. Okay. So you could think I'm going to talk about some theorems, but they're going to motivate the end of my talk. They're going to motivate why am I interested in doing certain things? Because those provide tools, theoretical tools, for solving problems like this, which are very, very deep questions. Okay, so and there are different things that come into the different tools, right? So I'm going to focus on one of the tools, which is I could probably do in about an hour. I can give a reasonable idea of one of these tools in an hour. So the last part of my talk will be talking about a tool that goes into proving this, and a tool which I think is, it's not a completely familiar tool to people in geometry. It's more kind of a tool familiar to people in dynamical systems or in topology. So, but it's not hard. It's not like hard. So I think we can understand it. So this result is good. So it says there's a number bigger than or equal to pi such that every one disk in R3 has radius at most that. So I'm looking for a compact embedded disk, constant mean curvature 1 in R3, then its radius can't be very big. Radius is the maximum distance, intrinsic distance, from a point on a surface to its boundary. So whenever you have a compact manifold with boundary, okay, you can talk about its radius. So here's a surface. You can look at the maximum. You can look at a minimizing geodesic from points in the surface to the boundary. So you can look at the distance to the boundary, and you look at the maximum distance of points in the surface to its boundary. So if you're in the plane and you're talking about a round disk, then of course the radius is nothing more than the radius of that disk in the plane. So this corresponds to what we call radius when we're talking about a disk in the plane. So, okay, so that we're going to talk a little bit about that. Right, immediate consequence is that result I was talking about with Giuseppe, right? Giuseppe Tenaglia. If you look at a simple exhaustion of the plane, that's just an exhaustion by disks that go further and further out. Well, the plane has certainly infinite radius, right? Eventually, these disks have to have big radius. Think of it's an exhaustion, right? Eventually, every point, any compact set is eventually contained in one of those disks. Anyway, so the existence of a plane would contradict the radius estimate. So there's nothing very hard there. Okay, the other thing is curvature estimate. So I'm going to state it this way, and then I'm going to try to state a different version of this, and I'm going to focus on that different version. So this is kind of an easier to understand thing. I have less constants. So I have an epsilon. Then given an epsilon bigger than 0, there's this a constant. such that whenever you look at a one disk in space, and you look at points which are intrinsically at least epsilon from the boundary. So you look at points, you have some kind of a disk. Okay, and you look outside of an epsilon neighborhood of the boundary. Okay, so you're looking at points that are at least epsilon away from the boundary. Then I have a uniform curvature estimate. Okay, so I look at, there's a uniform curvature estimate for the norm of the second fundamental form. Now in this statement, notice I have one disk. Okay, in a little bit, I'm going to try to get a much more universal curvature estimate. But this is sort of easier to understand, okay? Okay, so one of the ingredients that comes up in what I'm talking about today is this ingredient called flux. Okay, so if you have a simple closed curve, one cycle is just in this case, it's just a closed curve for me. On an H surface M, I can talk about the flux of that closed curve. Okay, and what I do is I integrate. I take the if this is an R3, I have the mean curvature of the surface. I multiply it times the curve. That's a new mapping. I can add the unit normal field. That's, again, somehow a curve in space. I can take the cross product with the tangent field to the curve. And I integrate that, and I look at the length of that vector. So I get a vector in R3. It's integrating a vector-valued function, say, on a circle, and I get a vector called the flux. And what's interesting is it's a homological invariant. So if two immersed curves are homologous, they give you the same number. Okay, and I don't think I need that thing about the annulus. Okay. All right, so here's the version that I want to explain something about its proof. So I'm going to explain something about its proof. There's an ingredient in its proof, and that's going to be a part of my lecture today. That's going to be most of my lecture, is a small ingredient in the proof of this result, of this curvature estimate. Okay? So, so what is this curvature? How is it different? Well, notice I have two numbers. I again have an epsilon, which is related to the distance to the boundary. Okay? But I have another number, delta. Okay? And that delta is going to be, delta is going to be the distance to the boundary, I'm sorry. Epsilon is going to be a bound for the mean curvature. So I want the mean curvature to at least be something. Notice that helicoids don't have curvature estimates. You can take a helicoid and homothetically shrink it, right? And the curvature will blow up at the origin, so you can have points you can be far from the boundary and have big curvature. So we need some kind of estimate to get a curvature estimate, which we need some estimate on the mean curvature. So that's where the epsilon comes in. So I want the mean curvature to be at least epsilon, but this constant is going to be universal, okay? So as long as I'm at least delta away from the boundary, I have a uniform estimate. This constant depends upon epsilon and, the constant only depends on, it depends on epsilon and delta. It depends only on epsilon and delta. So it gives me a curvature estimate for every H surface, every H disk, which is at least mean curvature epsilon. It's not the same theorem. It's really a different theorem than the other one. This is a better theorem. If you, for example, fix, anyway, it's a better theorem. Just take my word for it. Okay, so what are the ingredients? I'm going to talk about what this means, one-sided curvature estimates. In a second, I'll draw a picture about what that means. But the ingredients, one of the ingredients is what's called one-sided curvature estimates for H disks and homogeneous three manifolds. Okay. Okay, it turns out that one-sided curvature estimates lead to what are called weak chord arc estimates. So they relate intrinsic and extrinsic distances up to constants. But they only do it in a certain kind of way. Okay? So we'll see some what that means in a minute. But anyway, if I can relate intrinsic to extrinsic, and somehow I could know that they were comparable, then proving this really means I can prove it for extrinsic distances. So the distance we're thinking of measuring intrinsically, but now I want to do it extrinsically. So that means I can assume that our delta, our distance to the boundary, is an extrinsic. So here's my point at the origin, and its extrinsic distance, the boundary, think of the boundary of my disk is outside of the ball of radius delta. Then I want to prove that this disk at the point P, at the origin in this picture, the norm of the second fundamental form is not too big. So it's an extrinsic property. If I'm extrinsically far from the boundary, then I get a curvature estimate. And like I say, somehow the extrinsic one is interrelated with an intrinsic one via a way of measuring the relationship between intrinsic and extrinsic distances. That's a little subtle, but anyway. One of the problems here is the failure of the convex hull property. So if this was a minimal disk and its boundary is outside this ball, then its intersection with the ball would be a disk. This component here would be a disk. That makes life much easier. For us, all we know is that we have a planar domain intersection. Okay? And we can't ever, in principle, we can never guarantee that it's a disk. There may be no matter how small we pick delta, there might always be an example which is not a disk. Why? Because we don't know we have an estimate for the norm of the second fundamental form. Once you have the estimate for the norm of the second fundamental form, then it's true. There exists a delta so that this is a disk. But we don't have that estimate yet. So we don't know the local topology of what's happening here yet. After we have this theorem, we have this picture. Small deltas, this is a disk. But we don't know that. So that makes some parts of the proof more complicated. So really what you want to prove is estimates for planar domains with zero flux. Remember, the flux was a homological invariant. So that planar domain in the picture has zero flux because those curves also lie on a constant mean curvature disk. So that's one aspect. But it's very hard to prove estimates if the topology is not controlled. I say I have genus 0 surface, a planar domain here, but then I have to control the number of boundary curves. So with a lot of work, one can prove whenever you have a constant mean curvature disk, boundaries outside of a ball, any ball here. So if this is constant mean curvature, the number of boundary curves of this planar domain are uniformly bounded. So we can't have, for any constant mean curvature disk, this component, there's a bound on the number of boundary curves. So you have to think about why that's true, but anyway, one can prove it. One can prove that in general, no matter what the radius is. There is an upper bound. Okay, so that's one key step. Reduce the question to that. Now here's what most of my talk is about. Okay, so then once we've got our surface, what do we usually do? We try to rescale. We try to pick a point of almost maximal curvature. We somehow look at where the norm of the second fundamental form is very big, and we do rescaling arguments. And those rescaling arguments produce, so failure produces a surface, I don't know if I called it something, somehow a limit surface in R3 of bounded second fundamental form, bounded A of M. Okay, so in fact maybe less than or equal to 1. So we have bounded second fundamental form limit. The failure of this, we find points of almost maximal norm of the second fundamental form. We translate those to the origin. We produce then a surface in R3, which is clearly going to be a planar domain. It's a limit of planar domains. You have to check. This is going to be a planar domain, bounded second fundamental form. So a lot of my talk today is about understanding all such surfaces, even if they have, say, positive genus. Look at all complete embedded surfaces in R3, bounded second fundamental form, and assume that they have constant mean curvature. Okay, now why do I say constant mean curvature and not minimal? It's because I'm not assuming that there's a bound from above on the mean curvature. Right here. This mean curvature might be going to infinity. In order to fail an estimate, maybe it's true for constant mean curvature 1, but not true for constant mean curvature 1,000. The estimates get worse and worse. So because of that, when you rescale, all I know is that this surface has bounded second fundamental form and constant mean curvature. Maybe it's minimal, maybe it's not. Okay, so we're going to try to understand that, and we're going to do things to the surface. We're going to take this surface, and we're going to look at all of its limits. Okay, so when you take a surface with these properties, you can try to understand what it looks like by taking all of its limits. So I take a divergent sequence of points on it, I translate the surface to the origin, and I look at all those limits, and it turns out those limits form a compact metric space. And then I can study it a little bit more. Anyway, with a little more work, one can see that not only do I get this surface, but this surface has limits which are Delaunay surfaces. Well, if I have a Delaunay surface, you can check it has non-zero flux. But that contradicts the original planar domains that created it has zero flux. So that's one. There are other ways to do it, but that's one way. That's one way to do it. So we could get a constant mean curvature surface under scaling. I get a Delaunay surface, can't happen because of flux. I could get a helicoid, right? I could get minimal surface. I could get a helicoid, catenoid, or Riemann. Those are, by classification, those are the only other possibilities. So, but the Riemann example and the catenoid have non-zero flux again. So those are eliminated. So the only thing that's possible is a helicoid. So we could think of near the origin here, what happens is I'm going to have to see at the origin, at this point, or at this point P, I see on a very small scale a helicoid forming. Okay, and its part is contained on a planar domain whose boundary is in this fixed size, like a delta, so imagine like a fixed size ball here. And what a helicoid has, looks like a multigraph, right? And what you end up showing is that the multigraphs that form on the scale of looking like a helicoid actually go out a definite distance. So in some smaller ball, a fixed size, these multigraphs go out a fixed distance. But they get more and more of them, they have to accumulate, so they have to get very, very close to each other. But you can't do that. If you have a graph of constant mean curvature this way, remember the sheets of a helicoid are oppositely oriented. So I can find one that's pointed down and another one which is pointed up, and they're getting close as I possibly can get. You can't do this with constant mean curvature graphs. You can't make them be very, very close. There are various arguments for that, but you can't make graphs be close unless the mean curvature is pointing the same way. So you can't get helicoids, okay? So that's more or less the idea, right, this last idea. So you get a contradiction of the helicoid. So we eliminate this limit, and that limit by flux, and we eliminate this one by understanding extensions of multigraphs, which is quite technical. So anyway, it's technical for a number of reasons. It would be easier if we knew it was a disk. If we knew this original surface was a disk, it would make some of the arguments easier, but we don't know that. Okay, so I mentioned one-sided curvature estimate for H disks. That's this picture. Okay, so we have an H disk. Okay, and I want to think of it as a big H disk. So it goes near the origin, and it's relatively curved. The norm of the second fundamental form is like, anyway. Okay, so we have an H disk. It lives in a half space, at least inside this ball here. So the boundary lives outside of the top hemisphere of the ball, and we could be the boundary below, but it's above here. We don't know the topology of this. This could be a planar domain, right? It's just a portion of the disk. But anyway, what we get is a curvature estimate that works for any value h. Okay? All right. So there we go. So it has to look graphical when it approaches the plane. And the other thing is actual genuine chord arc property, okay, which says if you have an H disk and inside of it, so think of the H disk is at the origin, you have points on it that are very, very far from the boundary. So there's a uniform number here, which is C. So C times R, think of C as large. It contains a big ball. It's not necessarily a disk, but the ball centered at that point is contained in here. Assume that there's points with relatively big curvature. Okay, wait, assume that this is right. That relatively close to the origin, there are points where the norm of the second fundamental form are reasonably big. Okay, then you get a chord arc estimate. So as long as you're far away somehow. So in the ball of radius r. So in this, so I can get my mouth thing working. Is it the battery's not? Oh, there it is. So if you go out to distance r, then you obey a chord arc property. So you really start traveling away from the origin. So as you move away from that point, you move away from the origin at a definite rate. Once there's a little R naught here, but basically you move away from the origin at a good rate. Okay, so now I'm going to come back to the last one of the last things I was talking about in my last lecture. I was talking about this isometry conjecture. Okay, and part of it has to do with yes. What? Any mean curvature at all. Big curvature. Well, bigger than 1 over r naught. Right? Like if you had constant mean curvature 1, then you're going to have this at every point, right? But we aren't, right? So if you, for example, suppose you had a constant mean curvature 1, then what would this say? This would say, well, the norm of second fundamental form is like square root of 2 or something. So we'd be good shape, right? If you went out, R naught could be 1, for example. We just want, if it's minimal, you have some issues. You don't want really flat, you don't want to be the really flat part of the surface, like the helicoid. Over here, it's very, very flat. And then this point is far away from this point, right? It fails. So you have to be somehow reasonably close to points of relatively big norm of the second fundamental form. It's a scale invariant property. This is a scale invariant formula here. Okay. Anyway, right. Otherwise, it's not true, right? It's not true on the helicoid. So you have to assume that that you're not far from the axis of the helicoid, right? Or it's not true. So you need some kind of estimate that you aren't real flat, because it's false. Okay. So I just want to talk about this problem real quick we mentioned it last time. If you take a complete embedded minimal surface in R3, do intrinsic isometries extend to ambient isometries? Very nice question. It motivates a lot of problems in the subject, that problem. It sounds very isolated, but it actually motivates a lot of work in the subject. So to understand that problem, you need to understand something about all the isometric minimal immersions of a surface into R3. Well, all minimal surfaces are made by the Weierstrass representation. And then you want to say, well, if I have a given surface, okay, if you remember those formulas I wrote down last time in my talk, you can write down the second fundamental form and so forth. You can see that if you change this height differential by multiplying by e to the I theta, I get an isometric surface. It might not be well defined, though. If this has real periods, if I multiply by e to the I theta, and it's not pi, theta is not pi, then in general, I'm going to have the real part's going to be non-zero. I'm not going to get something well defined. Okay, so, but anyway, those are called the associate surfaces. I multiply by e to the I theta. If you're simply connected, there are no periods, in which case you can do the deformation. It's a one-parameter family of deformations that don't change the normal vector. The Gauss map doesn't change during the deformation. Okay, so those are called associate surfaces, and the theorem of Calabi says that if you take two isometric immersions of a disk, it's a local kind of question, of a disk in R3 that are minimal, isometric, then they always differ by being associate surfaces. In other words, after a rotation or reflection, they are nothing more than, as mappings, they're given as associate surfaces. Okay, I think I'll skip this. I don't have time to talk about that. Okay, so here's that conjecture. M in R3, a complete embedded H surface, then every intrinsic isometry of M extends to an ambient isometry of R3. A lot of people here are interested in homogeneous spaces. It's not true in homogeneous spaces in general, so this is really something about R3. Okay. Furthermore, if M is not a helicoid, then it's minimally rigid in the sense that any isometric immersion of the surface into R3 is congruent to that surface. To do that stronger result, it suffices to prove that the helicoid is the only minimal surface, complete embedded minimal surface in R3, and that's not the plane, with the property that it has no flux. The flux is related to the previous thing, is related to the periods here. So the claim is, somehow in here, is that the helicoid, helicoid's the only complete embedded minimal surface in R3 with zero flux. It's the only complete embedded minimal surface in R3 such that an associate surface is well defined. Okay, all right, so we know this theorem in lots of cases, which I'm not going to explain. I had this slide last time. But I want to talk about an aspect of that that's very relevant to our course. Okay, so let me try to connect our course to this conjecture. Okay, so suppose you have a complete embedded H surface in R3 with zero flux. Okay, like a complete embedded minimal surface with a non-trivial isometry on it has zero flux, minimal surface. Okay, then any local picture, okay, then we want a very general result, then any local picture M prime of M on the scale of topology. This is the scale where you pick points of almost minimal injectivity radius, you translate them to the origin, you rescale, and we had this very long theorem that I talked about before. That you get certain kinds of limits. You can get a properly embedded minimal surface in R3 with injectivity radius function bigger than or equal to 1 at the origin. Or you might get a parking garage structure limit. Or you might get this weird singular lamination limit. Okay, so just keep that in mind. That's what we're talking about here. Local picture on the scale of topology. It's one of those limits. It could be like a parking garage structure. But anyway, Now, once you take that surface, okay, then any local picture of that surface on the scale of curvature. So now we rescale such a surface on the scale of its second fundamental form. So if it doesn't have second fundamental form is non-zero, is unbounded, if it doesn't have bounded second fundamental form, then it's going to produce other surfaces, and those other surfaces are going to be helicoids. Okay, so why is this true? Why is this thing? Well, let's just look at what happens. If you remember that there were three possibilities for the local picture on the scale of topology. Either you got a parking garage structure, right? Parking garage structure, we also said we had connection loops, and these connection loops have non-zero flux. Non-zero flux in the limit implies non-zero flux on the original surface. But we said our surface has zero flux, right here. Okay. And the last possibility was we had the singular lamination limit. But on it, we also have connection loops on some planar leaf. Something spins. We get two spinning things, and we get connection loops. So again, we have non-zero flux. So the only option was the first option in that theorem, which is the local picture is a properly embedded minimal surface in R3 with, I'm thinking the minimal case. I should ignore. We always get minimal because this is fixed. Right? So when we rescale. Anyway, so the only thing that's left, okay, so we get this properly embedded surface with injectority's function bigger than or equal to 1 at the origin. Now, if it doesn't have bounded second fundamental form, locally, it's a disk. Locally in space, it looks like a disk. The only rescalings of it are helicoids. Right? All right, so, right, and remember, we can't get a helicoid in the isometry problem, right? If you got a helicoid, that would say the associate surface to the helicoid was embedded. Well, that just doesn't happen. It's not it just doesn't work. It's an it's an injective map. And associated surfaces of the helicoid are not injective. And they're not embedded in general. Okay, so anyway. So that's how we relate somehow the local properties to global properties. That's going to be the theme of the rest of my talk, right? We have a very special topic where we try to understand, for example, complete or properly, well, they're all going to be properly embedded surfaces in R3 I'm going to focus on the positive mean curvature case. Constant mean curvature, say positive equal to 1 if you want. Bounded second fundamental form. However, I'm not going to say what that bound is. You can scale it so it would be 1, but it's bounded second fundamental form. So that's going to be what we're trying to do. So I'm going to go now to my actual, this came out of somehow my talk at IMPA, and now I want to go to a different talk, which is I call it CMC talk. Okay. So this is going to be kind of nice. It's self-contained. Okay. So I'm going to start at the beginning. So think of this as almost like a new talk. This is going to be a very self-contained talk, okay? So hopefully it'll be better, kind of good for a course. Okay, so we had our Delaunay surfaces. It's good to know a little bit about them. They start with a cylinder, and there's a one-parameter family of them, and then they converge to a sequence of spheres. So as you go to the limit, you end up with somehow looking like catenoids joined by little, so it's like a collection of spheres along the line, and if you rescaled what happens when the norm of the second fundamental form blows up, you see a catenoid forming, okay, when you rescale. Okay, so that's those are those examples, okay. And as I mentioned before, the Delaunay surfaces are the model surfaces for annular ends. by Kushner, Korvar, and Solomon. These are the model surfaces. Annular ends are asymptotic to these, okay? And of course, here are just more pictures. Here's an interesting picture. You can actually have these trinoids with actually, you can have a cylindrical end. This one has, you see how quickly they change. Like, here it's a cylinder, and almost immediately it's a Delaunay surface. I mean, it's extremely quickly it goes to Delaunay surfaces. So one of the things you actually prove in their theorem is that when you're asymptotic to a Delaunay surface, the convergence is exponential. You converge very quickly to the Delaunay surface. So as a graph, the graphing functions converge to 0 exponentially quickly as you travel along the axis of the Delaunay surface. So it's not surprising that almost immediately they look like Delaunay surfaces, right? It's very hard to see immediately it's not a Delaunay surface. It looks like a Delaunay surface. And here's some more complicated ones. Anyway, you can make lots of examples. Okay. All right, so part of this talk is about focusing on these finite topology examples and this sort of theorems that we talked about before. So we have the Calabi-Yau problem for finite genus. That was a conjecture I mentioned before when we talked about Calabi-Yau. It says a complete embedded H surface in R3 of finite genus is proper. And I mentioned in that same talk, it's my hope that, there's a sort of the minimal case, which is these 3 people, and then myself and Giuseppe Tignaglia, we're more interested in, say, H equal to 1. And in that case, we actually think we have a reasonable chance to prove the conjecture. When H is positive, we actually hope to actually prove that you have cubical volume growth, cubical area growth. So in balls radius r, you have areas bounded by a constant times r cubed. So we actually have very nice estimates. So it's very, very proper. It's very, very nice. Okay, so, we know this conjecture in certain cases. If you have a countable number of events, it's true. Once you know it's proper, once you know you have proper, then annular ends have the cylindrical boundedness property, and once they're cylindrically bounded, it's easy to see you have to have at least 2 of them. You do Alexander reflection argument. So finite topology, you have to have at least 2. And then we have this nice theorem of Korvar, Kushner, and Solomon to say that once you know you're proper, then you have this, things are good. All right, and like I say, it's true for countable number of ends. So in particular, it's true for finite topology. So complete embedded H surface in R3 of finite topology, therefore a finite number of ends, in a finite genus, is always properly embedded. In which case we can apply these results. Now CMC, what I mean by CMC is H is not 0. So I'm going to be talking more about CMC for the rest of the talk. So that means, after scaling, that means constant mean curvature 1. So CMC for me means that. Okay, so starting at the beginning. So we're going to be looking at surfaces M. They're all going to satisfy this property. They're properly embedded CMC surface with bounded second fundamental form. So, okay, that's our category of examples. Now, if you have a properly embedded surface in R3, it separates R3 into 2 regions. And since it has positive mean curvature, we're going to be looking at CMC, positive mean curvature. It has one of the regions in R3 is mean convex. And I'm going to be always labeling that by W sub M. So that's the component on the mean convex side. Okay, and we're interested in taking limits. And we're going to see pictures in a second of surfaces, and we can understand what the limits are for some of these surfaces. In general, we're going to get limits with an infinite number of components. So we'll see that in a minute, but for the moment, we're just going to take the set of all properly immersed, not necessarily connected surfaces in R3, which are limits of some sequence of translations of the surface, okay, where the points go to infinity. So that means we're taking a divergent sequence of points. The points are going to infinity. So we're translating the surface from infinity, maybe this way, then this way. But we're trying to see, what does this surface look like at infinity? Well, it might look like different, depending upon which direction you go, it might look like such and such. You go in a different direction, it might look like something else. So we want to look at all of these pictures at infinity. And all the pictures are described in terms of this collection of surfaces. So one thing we need to know is that this somehow is a nice, reasonably nice surface. Notice I said properly immersed. Yeah, so I'll say a little bit more about that in a minute. They're essentially, they're almost embedded. They're what are called strongly Alexandrov embedded. Okay, all right, so now here's a different, this is a certain sub-collection of these limit surfaces. So this is a subset of these surfaces that go through the origin. Okay, but something bad happens. Like I say, these surfaces, here's the surface over here. In the limit, even though before you get the limit you're embedded, in the limit you might intersect yourself. So you might have this somehow a picture like this. So here's maybe in they're bound to second fundamental form, so always they locally look like graphs. But you could have this graphical disk and this graphical disk in the limit join up. So these limits, I also want to say they're pointed. They go through the origin, and they're pointed. So I picked that point that goes through the origin. But there could be 2 points that go through the origin because it's not embedded, right? So I would treat whatever the surface is here, depending upon which choice of disk I'm on, these would be different surfaces in here. So generically, there's a unique point going through the origin. That's not a problem. But if you had if it's not embedded at the origin, then it's going to produce 2 different elements in here because we pick a base point. Okay, so you could produce 2 surfaces with the same image surface in space. Okay, that's just a technical thing. But I want to think of it, I have a point on the surface, it's an abstract surface, and there's a point on it, and that point goes to the origin. Okay, so here's our very nice picture that kind of tells us what to do. So this is an example of a singly periodic constant mean curvature 1 surface in R3. How do we make it? Along this line here, I put a chain of spheres, and then coming out of here, I put chains of spheres going that way. And then I desingularize that configuration. So you have to imagine somehow desingularizing it, and I make a surface that looks like this. So it's almost like a Delaunay surface going up here, and then these spokes coming off of here are more Delaunay surfaces. So this is a surface with an infinite number of ends, and has genus 0, right? You can see this surface has genus 0. It's just there's no topology anywhere. Interesting topology other than the ends. Every simple closed curve separates. So that's our example. And then you can say, what are the limits I get? And it's singly periodic. So one of the limits is, since it's periodic, is itself. I could take the translations of it and bring those points down. So it's one of the elements in T of M, for example, or L of M. Okay, that's one possibility. Right. So either your translates of this, or you get a doubly periodic family of Delaunay surfaces. So if instead of translating up, you translate sideways. There's sort of 2 different ways to translate that are interesting, up or sideways. If I translate sideways, I just get a family of Delaunay surfaces, and I can translate in the direction of the Delaunay surfaces, or I can translate up. Okay, so right. So if you did it exactly the way I sort of imagine making this example, then it's actually a doubly periodic surface. Not connected, right? The limit does not need to be connected. Okay? Yes? I'm taking a divergent sequence of translations. I translate to the right. Yeah, we get a, yes. Okay. I didn't, L of M, they don't necessarily have to be any point passing through the origin. There's L of M, and then there's T of M. T of M are connected surfaces that go through the origin, and they have a base point. Right. Now, if I take the translations which I translate a point on the surface to the origin, then I'll get a surface going through the origin. But right now, L of M does not need to have any component that goes through the origin. These are all translation, divergent translations, not necessarily from points on the surface. Right. So you get sort of like a family of lines. And of course, depending upon how I did it originally, these are all the same Delaunay surfaces, up to just vertically translating them. So that's what I would get in these spaces. And like I say, it turns out I'm focusing my attention on this space, but this turns out to be very important in understanding this space. Surprisingly important. So for example, I'll give an example of why it's important to look at both things. One of the theorems I'm going to talk about is that, well, notice this surface has an infinite number of ends. Okay, so one of the really neat results is whenever you have an infinite number of ends, there's always a Delaunay surface in the limit. Pretty cool. And to see that, I really need to use this as well, and use properties of all the limits. So if there's actually a sequence of translations of points on the surface, any surface with an infinite number of ends, that limit is always a Delaunay surface. And that was very helpful over here, right? So in the genus 0 case, this either has finite topology, remember this was a genus 0 minimal surface. One possibility it has finite topology, right? Well, then it has annular ends. And by Kushner, Solomon, and Corvar, those are asymptotic Delaunay surfaces, and so clearly I can get a Delaunay surface. But maybe this surface has no annular ends. Genus 0 and no annular ends. Well, if it has not finite topology, no annular ends, then it has an infinite number of ends. But whenever I have an infinite number of ends, there's always a Delaunay surface for a limit. It's pretty mysterious at the moment why, but that's true. And we'll at least hopefully, I'm just going to go until the time finishes. So hopefully we'll get to some point where we say, oh, yeah, wow, that's really neat. I can see why I always get a Delaunay surface, at least for some sequence of translations. So that's where we're trying to understand somehow a particular class of surfaces on which we can prove lots of theorems. Okay, so that's our goal. Right. All right. Okay, so the first key thing is to get a fixed size neighborhood on the mean convex side. So for example, Harold and I, we did this many years ago. So if you have a bounded second fundamental form, constant mean curvature could be, minimal's hard, but constant mean curvature 1, then it's relatively easy to see that on the mean convex side of the surface, there is a regular neighborhood. So in other words, remember we have the regular neighborhood. We have the neighborhood at one side. It's a solid region. Then we want to, the points are, okay, uniform distance from M. Okay, let me just keep going here. It has a fixed size regular neighborhood. So, okay, so that means the line segments that go into the mean convex side. Well, we're going to see a picture in a minute, but you have somehow the mean convex side. Here's your W. The claim is if you look at line segments of a definite delta length, okay, they don't cross each other. So that means the exponential map on one side, restricted to the normal bundle on the surface, this submerses under the exponential map. So on one side, I have this sort of nice picture. I have this nice picture on one side. And immediately you get from that area estimates. Okay. So if you take a point on the surface, okay, then and you look at an ambient ball centered at that point, you can't have very much area in it. Okay. Okay. This is going to be a definite number, and this is going to be whatever it is. The area is locally bounded. So one consequence of having a regular neighborhood on the mean convex side is that you have local area estimates. Remember, we have global curvature estimates. Locally, we look like little disks, and we can only somehow get somehow the idea is that you have in the small balls you have either one or two of these disks somehow nearby. So anyway, okay, right. So that tells us why we get limits. So if you take a sequence of points on the surface, you do these translations. We have curvature estimates. We have local area estimates. So a subsequence converges, say, around the origin, and by continuity, you see you get a global, properly embedded surface again. Okay, sort of, it's a diagonal argument. You get convergence, 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 and take the right diagonal sequence, you get convergence on compact balls in R3. All right, and okay, and there's similar results for any limits, right? Anything you get in here. Okay, and this is the kind of the picture. So notice this is where under limit you might have touched yourself. Okay, if we originally assumed the surfaces were not properly embedded, but Alexandrov embedded. So in other words, they bound an embedded three-manifold on their mean convex side. We could have generalized the class of surfaces. We don't really need properly embedded. We just need embedded. So if you push in the mean convex side just a teeny bit, then it's properly embedded. It could take place along curves, true. Could in principle, yes. Okay. Okay, so here's our first cool idea. We're aiming toward invariance, some kind of dynamical property inside of this set T of M. So remember, T of M are connected surfaces with a base point at the origin. They aren't all limits, they're just certain components that are limits, okay? That go through the origin, and we picked a base point. Okay, so, all right. So the claim is that take a surface that's a limit of M. It's in here. Then, in fact, all of its related pointed limits are contained in T of M as well. This is not so surprising because if you're in a metric space and you take a sequence of points converging, anyway, you take a sequence of, this is a picture in a metric space. This is the idea. You're in a complete metric space. So you have a sequence of points here that converge to a point here, okay? And vice versa. These are converging to here, and so we have P1, P2, and suppose these converge to a point here. Then by being careful, we can choose the right subsequence so that here are the original points up here, so that we can find a subsequence of these points that also converge to that point. We just have to get real close to this point, and then really close to this point, and so forth, and those sequence of points will also converge to P. So it's just kind of a diagonal kind of way of thinking about things. So limits of limit points are again limit points. That's the idea. Okay, so but it's real crucial to understand what happens here. I said it like, of course it's true, but it's good to see why, of course, it's true. So we take a surface that's in here, okay? So remember how we got this surface. You could really think of, we took a sequence of points on sigma, not at the origin, going to infinity. We translate the surface, so those points are now at the origin. And I mean, didn't have to happen that way, but let's think of it, that's the way we could make it. Right, and we took that limited pointed surface. So we got a limit surface, and we take this particular component that's going through the origin. So it's just almost, if it's embedded surface, then that would be great. But we may have this little problem at the origin. We may have to make a choice of which base point we want to pick. Okay, all right. And so we have the origin on this disk. Okay, the compact disk. And with the origin, and I can think of this disk as being a graph over its tangent space, right? So the surface passes through the origin. Let's assume it's embedded at the origin. I see this little graphical disk, okay? Okay, so we have, remember, we have around the points Pn converging to the origin, we have other disks, right? And these translated disks are creating this disk, okay? But they're disks on sigma. So those are kind of like these points here going to this point here. But remember, these disks themselves came from disks on the original surface M. So we have the original surface M. So we can approximate these disks as close as we want by disks on M that were translated to make those particular disks. Okay, so these ones, okay, so these translated disks on sigma create the disk D. They're related disks, okay, which remember these come from arbitrarily far away. So we could, for example, choose points in here that are really, really far from the origin. They're much further away from the origin than this. And now you somehow translate those, and the distance, the Hausdorff distance between these translated disks and that disk go to 1 over n, and then those then limit again to f, to this disk on f. So we actually see that this disk on f came from disks on m that were going to infinity. Okay, and now we're finished, right? It's easy to see, but this is the Hausdorff distance. That means thinking of them as graphs, the graphs converge. So therefore, and the surface is analytic. If you know if I get the same disk at the origin, I get the same surface. So anyway, so we see that limits of limit points are limit points, and that's just this argument here. Then we're in a metric space essentially. And anyway, so that's what we get. So this is I call this the invariance lemma, right? Okay, we're going to use the idea on the invariance lemma later as well. So it's a good idea, not just using it, okay? So now we're going to talk about things that people talk about in dynamical systems. You have a homeomorphism, you have a diffeomorphism, and you can look at invariant sets, okay? So for example, the orbit of a point under the diffeomorphism, that's an invariant set. Diffeomorphism in all its powers. Okay, so that would be an invariant set. Okay, so it's just a standard idea. So we say that this is T invariant. This T refers to somehow this translation is T invariant if whenever you take a surface in that set, T of it stays inside. So T of sigma is a collection of surfaces, right? They are obtained by taking translations of sigma. Okay, and we'll just call such a subset T invariant if it has this property. In other words, the new limits stay inside of that set. Take any surface in the set, look at all these T limits, these pointed limits, then you stay inside the set. You don't go outside the set. Okay, so if you have a non-empty subset, it's called a minimal, a smallest T invariant set if it's T invariant and it contains no smaller non-empty t-invariant subset. Again, this is standard language from dynamical systems. The smallest invariant set, okay? All right, all right. And when you have a smallest invariant set, a minimal invariant t-invariant set, anything in it we call a minimal element. So if t of m, if you take a surface in T of m, it's called a minimal element if it's contained in some smallest t-invariant set. In particular, t-invariant set, all the elements of a minimal t-invariant set are minimal elements of T of m. Okay, so let's go back to our example here. Let's try to figure out what are the minimal t-invariant subsets of T of m. Okay, so we already decided that the elements of T of m, there are two kinds of surfaces. There is this surface, right, gotten by translating, or there's a Delaunay surface. Those are the only limits. Okay, that was right. Now remember we're focusing on connected. These are connected limits. Okay. All right. So that's any questions about that? Anyone get that? Certainly, if I take a Delaunay surface, it's easy to see that that's going to give me all of its translations. That's really a compact set of surfaces. Don't worry about base points. That's somehow the space is just you could take the Delaunay surface and just somehow on a fundamental domain of the surface translate through those different translations. Okay, so anyway. Okay, so this is, the next thing is just set theory. So it's really elementary. This is just a proof in set theory, but it's useful. It's a useful statement. And I think it also helps us think about things in this sort of dynamical point of view. So it's just something that's really obvious. It's just set theory, but it helps us when we're starting a subject like this. It's good to do the basic things. So it says, how do we characterize minimal t-invariant sets? Okay, so suppose you have a non-empty minimal t-invariant set. What does that just mean? I claim that it's a minimal invariant set if and only if, whenever I take a surface in it, T of that surface is the entire set. Okay, so the proof is just set theory. So let's just go through. There are two implications. Notice minimal invariant set implies this. This implies minimal t-invariant set. Okay, so we're doing the forward implication. So we have a minimal t-invariant set, and we want to show whenever we take a surface in it, then T of sigma equals the entire set. Okay? So you start out with one of these, take a surface in it, and we need to verify this property right here. Okay? So by the invariance lemma, right, T of that is a non-empty t-invariant set. Limits of limits are coming from limits. So a little thought shows that's what the invariance lemma was showing you, that this is a t-invariant set for any surface, any m. You always get, for example, a sigma that's in T of m. Any one of these surfaces creates a t-invariant set. Since it's minimal, T of sigma must, and it's invariant, must be the entire set. It's non-empty, and it's t-invariant, so it must be the whole thing. By definition of smallest, right? It must be the whole thing. Okay, so that does the forward implication. Now we want this sort of converse. So suppose you know whenever you have a surface, T of this is that, then delta is smallest t-invariant set. So this is also really easy. So suppose you have this property. It's a non-empty set. Whenever you take sigma in it, T of sigma is the entire set. Okay. Now notice that once you get this property, then you get its t-invariant because T of sigma is t-invariant. Okay. So now we want to show it's small, it's minimal. So take any other subset that's t-invariant, non-empty, and take any surface at all in it. Okay. Well, it's by hypothesis, this is a subset of that. So The surface is also in delta by containment. And the property is whenever you're in delta, you get T of sigma. But T of sigma is contained in delta prime. Therefore, delta is contained in delta prime, which means they're equal. Okay? So it's just set theory. Nothing very, very, very hard, but it gives us a way of sort of doing things. So it's interesting psychologically. So if you have a minimal invariant set, then notice it says that every surface that's in that minimal invariant set is a limit of any of the other surfaces in it. So there's a uniform somehow, right, you take any surface at all, right, in here, okay, then every other surface in there is a limit of it, and vice versa. So it's almost like being periodic. It just repeats itself in a very nice way. Okay, so anyway. Okay, so here's a crucial thing. We talked a little bit about this argument last time, that this is a compact metric space. And I just have to tell you what the metric is, and we have to understand that it's a metric space. So this is that picture I drew last time when I was doing, trying to explain, I think it was last time or the time before. So we have this picture. So we have these pointed surfaces, right? They have a uniform bound on their norm of the second fundamental form. So that means locally, the surface looks like a graph of gradient, some particular gradient, say gradient 1, and balls of fixed radius around any point on them, they look like graphs, right? Okay, so think of this as being the origin now. So take a surface in here, and suppose it's embedded at the origin. It's not going to be important because we're going to get away with it, but just suppose everything's embedded. Take another, this constant here is related to the norm of the second fundamental form. So if the norm of the second fundamental form is, say, less than or equal to 1, then there's a delta so that everything's graphical, and even maybe say gradient at most 1 over the tangent space. So we have this sort of graphical picture, okay? Such that, so now we have our two disks. So we have this disk, this blue disk on one surface. We have the red disk on our other surface. And those are compact disks in the ball. And now we just take the Hausdorff distance between them. So that measures the distance between the two surfaces. Okay? And you might think right away, well, it's going to be a compact metric space with this distance. You just think about it for a minute, but anyway, we're almost there. Sequence of graphs converge, right? And as long as they're, and if the Hausdorff distance between the graphs goes to 0, this sequence, the Hausdorff distance going to 0, then it converges to that limit. And we have, anyway, we have the invariance limit. So. Okay, so in general, maybe you're not embedded, but you still do the same thing. You make the same picture. You define the same distance function. The proof of the invariance lemma shows that every sequence in that has a subsequence which converges to another surface in it. Remember, every sequence has a convergent subsequence, and they come from M. They're limits of surfaces in M. All right? So that means this space is sequentially compact. Right? Whenever I take a sequence, I get a convergent subsequence. Really, I just do the convergence in the ball, and then I look at the surface in space that comes from that convergence. Okay? So that's a sequentially compact metric space, so it's a compact metric space. Now, the compactness I'm going to use after this is the finite intersection property that's equivalent to being compact. And so the finite intersection property says that if I take a collection of closed subsets of the topological space such that any finite intersection of those closed sets is non-empty, then the entire intersection is non-empty. So we're going to go away from this idea of sequentially compact and use this other equivalent property of being compact that's really for topological spaces. So we're going to kind of go away from metric spaces now, and we're going to focus on this other equivalent property. We're going to use that here. So every non-empty t-invariant, how am I doing with time? Oh, I got a lot of time. Okay, so I can go pretty slow. Let me go slower then. Okay, so we want to prove that every non-empty t-invariant subset of T of M, for example, T of M itself. T of M is t-invariant. So we're not lacking subsets, right? We have T of M. But just take your favorite t-invariant subset. Then it contains inside of it a smallest t-invariant subset. In other words, a minimal t-invariant set. It contains somehow the smallest one. Okay, so that's pretty neat. In particular, you always have minimal elements. And then a lot of the study, the deep properties of M are obtained by understanding these very special limits, which are minimal elements. They somehow repeat themselves in a very uniform way. And in particular, they might have to be Delaunay surfaces. Okay, so we're going to take a look at that now. Okay, so we start out with we're trying to prove this lemma, so we start out with our non-empty t-invariant subset. I'm trying to find inside it a minimal t-invariant subset, the smallest one. Notice the smallest ones are not necessarily unique. We have a partial ordering on subsets, containment. So a given, for example, T of M might have more than one minimal t-invariant sets. They might not they won't intersect at all, maybe, right? So in general, we're not proving anything about uniqueness. We're just proving existence. Okay, so take one. We take one. Go back. We're just trying to find a minimal invariant subset. In general, they aren't unique. Far from it. Okay, so then. Okay, so let's see. What am I trying to? I'm going to prove a couple things, properties of them. Look at T of M. That's inside of here. That's going to be a closed set in T of M, right? Closed just means we're in a metric space, so it just means that I contain all my limit points. Okay, and that's just the invariance lemma. Okay, so it's closed because it contains all of its limit points. All right. The intersection of closed sets in any topological space is a closed set. That's nothing to do with metric spaces. Intersection of any collection of closed sets in a topological space is a closed set. It's the opposite is the union of any collection of open sets in a topological space is open. So you take the complements and you get the related property for closed sets. Okay, so now the intersection of t-invariant sets is t-invariant. So that seems probably obvious, right? But let's see what the proof is. So take any collection of t-invariant sets that are in, it should be plural there. The intersection of t-invariant sets, any collection of t-invariant sets is again t-invariant. So take your favorite collection of t-invariant subsets, okay? And I want to look at a surface that's in the intersection. So I'm trying to show okay, I'm just trying to show that T of it will again be in the intersection. So how do we see that? What does it mean to be in an intersection of set? It just means it's in each one of them, right? The definition to be an intersection, by definition intersection, is that it's in all of the sets. But now we're going to use the fact that each of these sets were t-invariant. So since they're each t-invariant, T of sigma is contained in there for every alpha. But if T of sigma is contained in there for every alpha, it's also contained in the intersection. Right? So the T of M is contained in the intersection, and that is the proof that it's t-invariant. Take anything in it, and T of it stays inside. So you can think of a T as like a mapping that takes a surface into a power set. And we want the power set to lie in some other set. Okay, so we still haven't done anything. We've just done these first three properties. So we've shown that intersection, that the t-invariant sets are closed, intersection of closed sets is closed, and intersection of t-invariant sets is closed. And we're going to use those on a particular collection of subsets. So we're going to be looking at these kinds of subsets. So look at all subsets of delta, which are non-empty, they're closed, and they're t-invariant. Okay? So closed here could be a little ambiguous, but say closed in the ambient space, which is T of M. We also have the subspace topology, but anyway, I got it. Okay, and t-invariant. That's a collection of sets. What are we trying to find? We're trying to find a smallest one in this collection. Right? Remember, every t-invariant set is going to be closed. If you take sigma, t of it's a closed set. So anyway. Okay, so we're going to apply Zorn's lemma. That's the way you do these things. Okay, so it's just fine. I say Zorn's lemma implies there exists a minimal element for the partial ordering. But that's not true. You can't just say that's true. You have to make sure that somehow you produce something that is, again, in the set, right? You don't want to produce the empty set, for example. Right? So how do we know that every chain, let me just remember what happened. So what does it mean? To apply Zorn's lemma, we have to show that if you take a non-empty, totally ordered set, the ordering is by inclusion, then we have to show there's a lower bound. And these kinds of problems, a lower bound is obtained by taking the intersection of the totally ordered set. Okay, so why is that non-empty? Okay, so why if you have a totally ordered set is this non-empty? Well, remember, this is a collection of closed sets in the topological space. And the topological space is compact. Okay, so we just need to verify that that collection satisfies the finite intersection property. In other words, if you take a finite collection of sets, so if you take a finite collection, say delta 1, delta 2, anyway, finite collection in this total ordering, that the intersection is non-empty. So that's the standard thing. So if we have a delta 1, delta 2, a finite number of them, since they're totally ordered, that means these are ordered, right? Delta n, we have a finite number. We have to verify the finite. Since we have a totally ordered set, we have a picture like this, then this is the smallest set. This is the intersection. And by assumption, it's non-empty, because each of these are in lambda. So we satisfy the finite intersection property. Since we're in a compact space, topological space, the intersection of the entire collection is non-empty. So we're using that kind of, again, it's very standard in dynamical systems. This is the way you do things in dynamical systems. Okay, so that's why we can apply Zorn's lemma. We're using a finite intersection property and the fact that space is compact. All right, so we're getting close to there. Let's see. So we have a minimal element. We just have to show that a minimal element in the partial ordering is, in fact, a minimal invariant set. Okay? Well, of course, it's t-invariant because it's in lambda, right? So that's easy. And now we just have to show it itself is t-invariant. Okay, so I'm sorry. So I want to take so it is of course t-invariant. Okay, so gamma prime, take a minimal element in here. So that's a subset, minimal in the sense of the ordering. So take any other subset that's t-invariant, we have to show that it equals this, right? It's the smallest one. So whenever you have one inside of this t-invariant, it's equal to it, okay? So take a surface in this possibly smaller set, okay? So T of sigma is in this collection right. It's limits of limit. This is t-invariant, so this is going to be anyway. You check that this is in lambda, okay? So sigma prime. Right. It's in lambda, and but remember, delta prime was a minimal t-invariant set. So therefore, delta prime equals this, But since that was an invariant set, it's a subset of delta prime prime. So if delta prime prime is contained in delta prime, then and delta prime is contained in delta prime prime, that means they're the same set. It's again just set theory. Okay, all right. So that means that minimal element from Zorn's lemma is in fact a minimal T invariant set. As you can tell, nothing very deep in any of this stuff. It's all kind of elementary reasoning. It's an interesting point of view, but everything's nothing deep. There's nothing deep so far. So we want to start getting, interesting, not obvious applications of these ideas. Okay, so here's the general theorem. You could do this. There's nothing special about R3. You could do all this in a homogeneous manifold. You could do this in codimension. You could do this in Rn, for example. You could do it in hyperbolic n space. So there's a great generality of everything we did was very, very general. There wasn't much going on there. So you pick a base point in your homogeneous space. You have a transitive group of symmetries. Then you look at all the translations from divergent points on the surface. So you have points going to infinity. You translate them back by this transitive group of isometries. You look at all their limits. Okay, in order to know you have good limits, you need to know that the original surface has a fixed size regular neighborhood on one side, so you have local area estimates. We're assuming local curvature estimates, right? Bounded second fundamental form. So we immediately get compactness results. So it's a compact metric space. It has a natural metric on it. Same metric. We do this around the base point. We have a disk. And we have the Hausdorff distance. Okay, and anyway, nothing special. So, but this is just a summary of what we know, what we showed in R3. What? You could also, if you could have taken the whole isometry group in R3, if you wanted. Not very interesting for us because all the things that fix the origin are just a compact group of symmetries. So if you allow more symmetries, you just enlarge in the space by, like if you know what the other one was, now you just take all rotations of it. So in our other case, we had Delaunay surfaces, like in the other picture that we had before, we got a Delaunay surface. Now we're getting all rotations of a Delaunay surface. We're really not getting anything interesting. So it's kind of nice in this problem to make this small rather than bigger. It doesn't really add anything because you get all the other things by taking the stabilizer subgroup and just moving the T of m you got from the smaller group. Does that make sense?
Yeah, it certainly makes sense, but when you have like H2 cross R with that symmetry to different nature, it's not at all clear that one subgroup you take is a different thing.
You can take any transitive subgroup, any transitive group. Any transitive group, you have the theorem. If you want, you can take the entire symmetry group. Then, right. It's more interesting not to take the entire symmetry group, but you could, of course, once you do any group, then you also know what it is for the entire symmetry group. Just take that, and you can take at this base point, you then just move it around by the symmetries that fix that base point. You don't really get anything very interesting. Because everything's compact that fixes a point. All the symmetries that fix a point is compact. So you don't get really anything interesting. It doesn't help you for applications. The more restricted the group you use, the better maybe the applications. You don't want to take a really big, you want to take a small, if your symmetry group is dimension 4, you probably want to pick a 3-dimensional subgroup. And maybe later on you want to pick a different transitive acting 3-dimensional subgroup. You might get more interesting data by picking smaller transitive groups, right? Yeah, sure. You could. Well, one of the problems in H2 cross R is to do the same theorems that we were talking about before. Namely, if you have a surface in here, okay, say even specializing annulus, And let's assume that the mean curvature is bigger than a half. Okay, so you have a surface in hyperbolic H2 cross R. You have a complete embedded annulus in here with mean curvature bigger than a half. Problem 1, prove the Calabi-Yau problem. In other words, prove that such a surface is always properly embedded. In R3, we know how to do that. Almost certainly true. Nobody knows how to prove it. Okay, so let's suppose then it's properly embedded. What should it be? It should be a Delaunay surface. And what is a Delaunay surface in H2 cross R? Is you take a geodesic and you take a surface of revolution. You take a, not revolution, but you take a surface, a periodic surface, stays a bounded distance from this, is periodic under translation along the geodesic. So that's the claim. That's the moduli space of these surfaces. So first you prove they're properly embedded, and then once you prove they're properly embedded, then you prove that they're in fact periodic. And once you do that, then the claim is I actually know how to make these surfaces. And they all have a plane of reflective symmetry, a vertical plane of reflective symmetry. That breaks the surface into two simply connected pieces. And then you go into the correct Berger sphere. And what you see there is, you should see is that you take two geodesics and Berger sphere, they're linked, and you get an annulus. Somehow these surfaces should come from taking a pair of geodesics, I guess they're horizontal, a pair of geodesics in Berger spheres, solving Plateau's problem, because all these are going to be stable graphs, solve Plateau's problem, take the universal cover, go back into H2 cross R, I get a periodic surface. Claim is that that's how you make all of these examples. They're gotten by solving a Plateau problem in a Berger sphere.
Do you know what property embedded annulus is physically bounded?
What?
Do you know that it's physically bounded?
Yeah, you know things like that. In fact, you know things like that. What? Oh, you do know that, yes. Oh, I'm sorry. All right, you need to know some properties. For example, I would like to apply this theorem. Here's my example. Suppose I knew I had bounded second fundamental form. So part 1, prove I have bounded second fundamental form. That's true. You can prove the flux is, you have a flux on this. Rescaling would then produce flux in R3. Anyway, a little thought doing on the scale of the injectivity radius implies that such an annulus has positive injectivity radius. Once I have positive injectivity radius and the mean curvature is positive at all, I have bounded second fundamental form. I have the curvature estimates for constant mean curvature disks in R3. I also have curvature estimates there. So this surface, once I have it, this annulus, in fact, I guess I actually see the original annulus has bounded second fundamental form, even if it weren't proper. So every such annulus has bounded second fundamental form, presumably is proper. And now it has bounded second fundamental form. If it were proper, it separates. I can do this. I can look at limits of it. And so we want to understand what are some special limits of it. So I can take limits of it, and I claim the limits of it, maybe they have nice properties, like more symmetries. Remember, if I get a minimal element, every limit is, there's sort of two ways to go to infinity on the annulus. So you can go take limits from translations this way or the other way. There's sort of two kinds of things. And you try to understand it from the point of view of what I'm trying to do here. I know it's a bounded distance from an annulus, yes. Okay? And I talked to you about this at Boozio's a few years ago. Never been written up, but it is cylindrically bounded. And you said, oh, can you really prove that? We talked about it at night one night. And also that you have a vertical plane of symmetry. Yeah, okay. So anyway, continue. Okay, so this is good. This kind of thing works in some fairly good generality. And so far, nothing deep. This is a useful result, but in a sense, there's nothing hard about the proof. We're talking about something deep, which is a very useful tool. Okay, so I'm not trying to. Okay, so this is where things get more interesting. A minimal element theorem, at least in R3. So let's see what happens. And I didn't state the entire theorem. I didn't know I was even going to get this far. Okay, so minimal element theorem. So you have your surface. Remember, it has bounded second fundamental form in R3, properly embedded. So we have an assumption. This is our CMC surface, right? In this case, you even can allow yourself to have compact boundary. Because we're only interested in limits from infinity. So you can look at ends of a surface. We don't really, nothing essential anywhere about the surface having no boundary. It wasn't important. So anyway, but you can still take the limits at infinity. Those surfaces have no boundary. All the boundaries disappeared. Okay, and now we want to take a minimal element. That means it's in a minimal invariant subset. So this is a T-invariant set. The whole thing's T-invariant, and we just saw that we always have minimal elements. That was a general fact. Okay, well, here's something that's not very obvious. That's actually very not obvious, at least when you first think about it. Now, when I take all of its limits, which is this set, I don't get anything, and you assume that these are, okay, so I guess when I originally defined this, I want always one component of this to go through the origin. So remember, you could take all translations, or you could take translations from points on the surface. So if I do it from points on the surface, then there will always be some component in here going through the origin. There might be lots of them, but anyway. Okay, so what this is meaning is that the surfaces you get are connected. T of sigma are these connected components going through the origin. So you don't get more components. Okay? If your minimal example has at least two ends, it's a Delaunay surface. Well, that's also not obvious. So we're talking about deep. These are fairly deep things. We're going to see why. There's a technique, actually a technique motivated by some stuff that Harold did with Antonio Ross, and I also had some things in that direction. There's a technique that allows you somehow to get results like this. So that technique is also going to be important for us. Not an obvious technique. Okay, but once you get, I get why this technique is useful. Okay, so if you have at least two ends, then we're a Delaunay surface. Wow, that's pretty cool. The surface is chord arc. Now, chord arc means we can relate the intrinsic distance to the extrinsic distance. Now, it's actually genuinely chord arc as long as something bad doesn't happen. Remember, this surface, for example, might, at the origin or somewhere else, it might intersect itself like this, right? So I think of the surface as an abstract surface, right? So if it touches itself like this, there's no way you're going to get chord arc, right? These points are distance 0 in space from each other, but they're different points on the surface. So there's nothing, this problem because, so I guess I could say it's chord arc as long as I don't have any limits like this. As long as T of sigma is always embedded surfaces, then I could say chord arc. So otherwise, I have to just do something really silly. I only get chord arc when I say the points are at least some distance away from each other. So the number I picked, at least distance 1 away from each other. Then I have a uniform constant. So then the distance on the surface is comparable up to a constant. Maybe it's a big constant. And maybe it depends on the minimal element. This constant depends on sigma. Okay? Well, it's related to the second fundamental form, but you could have minimal elements in here where this C has to get bigger and bigger. So it's a constant that depends on sigma, right? But it's globally true for any points on the surface. Okay, so there's a comparison. So, okay, if you think about why, this is really nothing more than sort of this. If this were to fail, then you could see that you could make an L of M with more than one component. So this is really almost nothing more than this statement. So if the points were far away from each other in space, intrinsically, but close in space, then by taking such points, I could make two components. I could make two different surfaces. In order to get from here to here, I'm going to have to go almost to infinity, and the limit, I have to go to infinity, which means they're on different components. So this is actually a trivial consequence of that right there, essentially. Okay. All right, so anyway, that's a pretty cool result. And I'm going to at least try to get to some of the ideas that go into its proof. There's one theorem called the annular end theorem, and that's very deep. And I'm not going to, the proof is on the slides, but I know it's really hard. I'm not going to do that. How much time do I have left? I have 10 minutes, right? Okay, so this is a really good technique. This is something that Harold told me about. I don't remember if I thought about it myself first, but anyway, we approached this a little differently. So I say that they had this result, but it's related to something that they have. So you look at suppose you had our M over here. Remember the M we got over there. Suppose it was in a half space. Suppose it was in the upper half space. Okay? Then the claim is that there's some limit in here, okay? Not only just a limit, a minimal limit, a minimal example in here that has the x1, x2 plane as a plane of Alexander symmetry. So I can translate, and somehow I produce a limit surface that has a plane of Alexandrov symmetry. What that means is there's a plane, didn't explain what plane of Alexandrov symmetry was, but basically that just means the following. Bounded second fundamental form. So you know how to prove this. So it's with this other language. But it's more language here than you usually think about. But okay, so what this means is there's a limit surface. I have the x1, x2 plane here. And basically, I have a domain on it. For example, I'll do the picture for a Delaunay surface. So a Delaunay surface looks like this, and so forth. Notice it has a horizontal. If it's periodic and a horizontal line, then if I can cut it in half, and it breaks into a graph over its projection in the xy plane above and below. So that's what, if you want, that's what I mean. I have a symmetry plane that decomposes the surface into two pieces, and they're each graphs over a domain, the same domain in the x1, x2 plane, like a Delaunay surface. Okay, so this is a technique. Think of this. This is not like so important for us, other than it's a useful tool. So in order to apply it, before I prove it, go talk about the proof, how would I get this from limits? So let me just go to the next theorem. Large ball lemma. So let's look at the large ball lemma, and then we'll come back and say, that's an interesting, it's interesting to understand that last theorem. So sometimes that's good. So I want to motivate why we're interested in that last theorem. You could think, oh, well, that's just, okay. Why would I care? Oh, this is the reason why we care. This is the large ball lemma. So think of, and you have to apply this in a clever way. So you have to apply this in a clever way. So imagine I should draw it like this. Here's my surface in space. Okay? Now maybe it's the case, and this is a solid region. Think of this as a solid region U-bound, kind of. Suppose I could find balls in the complement. Well, of course I can find balls in the complement, right? So I take a point in the complement, and I just take a bigger and bigger ball until it touches the first time. I'll take a biggest one, so it must touch in several points probably. Like, otherwise I could make it bigger, right? Maybe over here as well, right? So maybe this ball touches in 3 points. Large ball, that means the radius, I want the radius of this ball to be really big. Okay? Suppose, like Delaunay surface, I can find huge balls in the complement of Delaunay surface. It just stays about a distance from a line. So they're balls of arbitrarily large radius in its complement. Okay, so let's think. Well, now of course I can't make the balls too big. Well, the center and this point are going to, I look at one of these points. I think of P1, R1. And then later on I find a bigger ball and a point, P2, R2. Okay? So what if I pick this divergent sequence of points to translate the surface to the origin? Well, what do I get? I get a surface of constant mean curvature as a limit, which lies in a half space, right? If you take a sequence of balls going through the origin, the boundary of the balls go through the origin, a subsequence, and the radii go to infinity, a subsequence converges to a half space. Okay, and so this could be why we're really interested in that last theorem. Because if I can get limits in a half space, somehow from balls in the complement, then I should be able to produce limits which have a plane of Alexander symmetry. So this is why we're interested in that last theorem. So it's why it's really useful. Because when you have a plane of Alexander symmetry, it's easier to understand the minimal elements, which allows us to prove, again, the deepest result that I have on the subject really is about surfaces which have a plane of Alexander symmetry. You might think, well, that's all kind of trivial. That's where it really is hard. But you can still prove things. They're just deep. Okay, so how do you prove this? What's the sketch of the proof for this? So I have the surface in a half space. I'll draw it one-dimensional, kind of one-dimensional picture. Okay. Oh boy. Okay. So here's the surface somehow. And I have it in the smallest half space. So there are points. I can think of points on the surface that are getting very close to the plane. Maybe they even touch the plane. Okay? There's no maximum principle here. But think of them maybe getting close to the plane. So when they get really close to the plane, because they have bounded second fundamental form, they're graphical over the plane. And don't forget, I also have a regular neighborhood. So I could imagine chopping off by a parallel plane close by. I could reflect in that parallel plane, and that graphical sort of local picture reflects into even the regular neighborhood, or certainly into this region W on the mean convex side. Okay? So I can take those points, I can try to take the plane that's somehow highest up when I do this, and I'm not going to explain the Alexander reflection principle, but we'll see how it works here. So you find, a highest value so that the part that lies below it is graphical, and yet their sequence of points going to infinity, not where we're horizontal, but where we're vertical. There are points where the tangent plane becomes closer and closer to vertical. Okay, so you have these graphs. The graphs are converged to a graph, but we have this vertical plane and then you apply the Hopf maximum principle at the boundary of that reflected image. So anyway, you see that these translated surfaces end up having a plane of reflective symmetry. Okay, and once you have a surface with a plane of reflective symmetry, that's clearly all the minimal elements associated to it have the same plane of symmetry. That doesn't change. So we produce a surface that has a plane of reflective symmetry, and if you take an M that has a plane of effective symmetry, all of its translates have the same property. So it always translates so the plane of symmetry is at the origin. So anyway, that's easy. Okay, so we get these minimal elements. And I just kind of explained why this was useful and how it worked, right? Okay, so now we have, if you have balls of large radius, then T of M has a minimal element with a plane of Alexander symmetry. And that's just that argument I was talking about before. We produce a limit that lies in a half space, and then we apply the previous theorem. Okay, now here's where you have to think a little bit. I want to apply somehow this ball lemma to this situation here. So if T of M does not contain a minimal element with a plane of Alexander symmetry, two possibilities. Does, it doesn't. Then there's an integer k such that the number of ends of M, or of any limit of M, maybe it's disconnected, has at most k ends. Okay? In particular, at most k components here. Because each one of them, assuming everything's compact and originally, so every component, in fact, has to have an end. So in particular, the number of components here is going to be bounded. This is assuming you have no plane of Alexander symmetry for any minimal element in T of M. And basically, this is related to finding balls. Because if I have lots of ends, let's see if I can remember. I think I actually have the sketch of, oops. Oh, shoot. I think this is more or less the proof. I'll put the whole thing up there. If you have lots of ends, then I can make a big ball, and I have all these ends that never get connected up after this. Well, these ends, remember they have a regular neighborhood. They occupy volume in the space. And if you had more and more and more of them, it turns out I can find not balls that are disjoint from the entire surface, but balls of large radius that are disjoint from a particular one of these ends. I can find bigger and bigger balls by using the volume constraint. Remember, there's a relation between the volume and the area. And anyway, so presumably this has been filmed, and Lucy will have a copy of this. So anyway, so you can look at the sketch there. And I'm almost there. This would be the last slide I show. Okay, so let's see. How do we get, remember, this is used in proving the minimal element theorem. When we say we have more than one, if we have, what was it, at least two ends, then we are in your minimal element, then you're a Delaunay surface. So there's this quite deep result that says if M has a plane of Alexander symmetry and at least n ends, okay, then it has at least n annular ends. Doesn't say that you don't have more. I mean, you can think of examples where you have infinite genus, and you have a finite number of annular ends. But if you have if you have lots of ends, then you can also find annular ends. Okay. Anyway, it's been a while since this is papers published in JDG a few years ago, so I've kind of forgotten about some aspects of the proof, but anyway. But the correlate is that if you have a minimal element, then each surface in here has at most one end, or else it's a Delaunay surface. Okay, so why is that? I'm forgetting now. But that's a corollary of this. It's a minimal element. Oh, right. That each surface in this has at most one end. Right. If you have a plane of Alexander symmetry, right, and you have more than one end, we have an annular end. And then you're asymptotic to a Delaunay surface, and then you have Delaunay surface limits, okay? So that means we don't have a plane of Alexander symmetry. And I don't know, I've kind of forgotten. Here's supposed to be the sketch of the proof. I kind of this morning just kind of got right before here when I was reviewing. I kind of did some typing last night, but I didn't really study the proof. But anyway, it's there. And I guess all this other harder stuff is there too. I'll give it to Lucio. If you're interested in it, you can read how you get the annular n proof and stuff like that. It's a long lecture. But anyway, that's it. I think I'm kind of time-wise finished. So, any questions about this? Anybody, or final kind of questions about anything? So it's neat when you have an elementary tool. It's very easy to apply the tool. Any surface produces something. Then you want to say, what are the most interesting limits? And that's helpful in understanding the symmetry conjecture. It's helpful in doing this problem. You find out that, taking limits and proving there exist interesting limits is very important. You have a problem, maybe in general question, you can say, if I can prove it in a very special setting, bound to second fundamental form, whatever, properly embedded, very, very nice, then I can prove it in general. Prove it in general. Okay, so that's it.
Thank you very much.
All right. Be back in July.